Welcome to Itasca Water's Practical Water Wisdom Series. I'm Brian Whittemore, your host for today. Today's program is mining and water quality and how the two can live well together in northern Minnesota. It's going to be an exciting hour, so stay with us. First, let me tell you a little about Itasca Waters. We are a local nonprofit headquartered in Grand Rapids, Minnesota, with members who either live or vacation in our area. Our goal is to continue to find interesting ways to educate residents in Itasca County about how to keep our water clean for both the environment and the economy. We've been teaming up with like-minded people and organizations for 16 years. You can read about those projects on our website at itascawaters.org. If you have an interest, please consider joining us and becoming a member or a volunteer to help support programs just like this. We thank our partners shown on your screen for their support in producing this program. Now, today's program will work as usual. Our guest will speak for about 30 minutes, and then we'll answer questions from you. To submit a question, you only need to click on the Q&A button at the bottom of the screen and type in a brief question. You can do this at any time, and we will read the question on your behalf. We will not be using the chat function. This program is being recorded and will be available for viewing online through our website, itascawaters.org. Also, we do value your opinion, so please click on the survey link, which will be on screen at the end of today's program, or complete the survey that will be sent to you by email. Okay, Dr. Patrick Schaaf is a Wisconsin native and attended the University of Wisconsin-Stevens Point, where he graduated with a BS degree in biology in 1976. He received a PhD in zoology and physiology from the University of Wyoming in 1981 and spent the next dozen years or so at the University of Wisconsin as a postdoctoral fellow at the Enzyme Institute and as a research faculty member in the Department of Meat and Animal Science, where he performed studies on developmental reproductive physiology. In 1995, he joined the Natural Resources Research Institute at U of M Duluth and worked on methods of targeting reproduction in invasive species. Dr. Schaaf's current research includes studies on the effects of chemicals and other stressors on the early developmental stages of fish and amphibians, endocrine disruption, and recently, sustainable development. Welcome to Itasca Water's Water Wisdom Series, Dr. Schaaf.
Thank you very much, Brian, and I'd like to thank the Itasca Waters for this very really kind and pertinent opportunity to talk about an important subject. I just want to mention that the title of this series is most appropriate. I think we'll find that is practical water wisdom. We're going to find many connections in today's talk. I'm not quite so sure about the wisdom part, but the practical part, we will find some connections there. So let me give you first, before I get started here, let me give you a quick introduction to NRI for those of you who may not be familiar with us. I'm trying to change screens here. Here we go. We were established by the legislature in 1983. We were actually established by the legislature for the legislature. The charter is to foster the economic development of Minnesota's natural resources in a sustainable manner to promote private sector employment. So maybe you can see right there where we start to get into this the practical side of things. We take this charter very seriously in our research. Our core values are probably familiar to anybody who has been in an industrial setting or a business setting or even an academic setting. We also take these quite seriously in everything we do. Our mission and vision are, again, pretty straightforward. Our mission statement, the first four words there are really what we focus on. We deliver integrated research solutions. We are in the business of delivering solutions. We do research as a matter of what we do. And this is a good opportunity for me to say a couple of things. First of all, I want to acknowledge that we at NRI and the university recognize that the land and the resources that really form the basis of our existence have formed the home of the indigenous peoples that in the area who have lived here from time immemorial. So we conduct our research with gratitude and a bit of humility as we go forward. Second thing, Brian mentioned my background a bit. I have done quite a few things in different scientific realms, but I want to make sure as we get into this subject of mining and water, and of course everybody realizes that this can be contentious. There's some touchy issues that occur. If I do venture an opinion, it is my opinion on a professional basis, and not the opinion or the practice of the University of Minnesota. Okay, so with that, just a little bit about how we work at NRI. We deliver solutions. We sort of categorize our overall mission in three areas. We call them initiatives, strategic initiatives: iron and minerals of the future, and ecosystem resilience, which are two subjects that we'll be talking about today, and then future forest industries, another broad category. Where we do our work is really kind of where these things meet. We innovate, again, solutions. What we're trying to do is recognize that all of these subjects fit together well, they intersect with each other and interact with each other. So any solution that we come up with has to address all of these different aspects. So with that, let me move into today's subject, which is how mining and mineral processing. By the way, I added mineral processing to this title just because it's, well, they go together. Mining and mineral processing are fit together. We see here just some examples of a mine itself and of a processing facility. But I just want to make clear that we're going to be talking about technological approaches to these questions, whereas the actual impacts and the question of how do we get along, or how do these two aspects get along, really are impacted by many more things than just technology. First of all, there's legislation that filters down to regulation, and then the very important community and socioeconomic aspects that really, frankly, allow these industries to operate. We won't be talking about any of those today, and so we may be able to bypass some of the tension or contention, but we'll stick to some technologies. In addition to the mines themselves and the pit lakes that occur, after mine closure, the processing, we also have issues of water in tailings basins. We also have issues of water from mining areas and from the landscape in general, moving through municipal and industrial wastewater treatment plants. Finally, the water ends up in receiving waters, either lakes or rivers, and impacts the biota, the plants and animals that exist in that landscape. The major questions that I think probably everybody on this webinar would be able to recognize. The major issues and concerns in Minnesota involve sulfate, mercury, and other heavy metals, there's a lot to do with process water, and this I'll be talking a bit about that near the end of the talk. And then, of course, the physical location of the processed water in tailings basins and in pit lakes. So with that, I want to talk about a few technological approaches, starting with sulfate. So this map you may be familiar with. This was put out by Amy Merble from the University of Minnesota a couple of years ago, and her colleagues, showing, and what this shows is sulfate levels throughout the state. There are the points are the presence of wild rice, but just concentrate on the map itself and the colors. And you see, if you look at the key, it might be a little hard to see, but the blue is very, very low sulfate, and it gets progressively higher as you go from blue to red. And in fact, if you track from northeast to southwest, you can find that same increase in sulfate values. The low sulfate values that are in the northeast part of the state are really quite low, 0 to 5. This is all in milligrams per liter or parts per million, whereas levels in the southwest part of the state can be very, very high, up in the over 2,000 milligrams per liter or parts per million. We, of course, see the area that we are in right now, or very close to, and the area that's pertinent to our discussion this afternoon, the mining area, specifically the taconite mining area in the range, has, as you know, a higher sulfate level, and therein lays the problem, particularly when it comes to the wild rice standards. The notes on the left are important to realize. Sulfur is a natural element. It's part of living systems. We need it, not in large quantity, but we have, or all life has evolved within the presence of sulfate. So in most cases, sulfate is a kind of a non-issue or a very slight issue when it comes to health and well-being. Natural sources of sulfate in rocks, of course, which explains why it comes out in mining operations. Agriculture, lots of fertilizing and dealing with chemicals in agricultural settings releases sulfur. Industrial processes, of course, and a fair number of consumer products can contain sulfate, and that can enter the water stream. As we know, wild rice is extremely sensitive to sulfate under certain conditions, and therein, well, that is part of the context that we have to deal with looking at controlling water quality in mining areas. That sensitivity to sulfate led to Minnesota's sulfate standard, which is 10 milligrams per liter or 10 parts per million in areas where wild rice is present. Now, this is one of those areas that once again, we don't deal with those definitions here at NRI. We see this as an issue that needs a solution, so we go on from there. What we see in Minnesota, and you can see from this map, is that it's not just mining areas or even industrial areas that need approaches to sulfate remediation. We have really, for just our organizational level or reasons, we kind of split the sulfate issue into three, buckets, as you can see here. Municipal water facilities, treatment facilities, usually deal with waters with between 50 and 250 milligrams per liter sulfate. That's one bucket. A second bucket, so that's a fairly low concentration. By the way, just once again, this is not my field, but humans can tolerate those levels, that low level of sulfate really well, and frankly, usually don't even notice if it's in water at that level. A moderate level, 250 to 2,000 milligrams per liter, moderate to high, is commonly found in agriculture, industry, and in our mining pit lakes, where sulfate gets a chance to accumulate over time as water fills those spaces. And then very high sulfate levels are sometimes seen in power plants and must be treated in their effluent. So as we approach this question of how do we remediate, how do we address the sulfate problem, we often look at it in this idea of, well, sometimes we call it a sulfate remediation chain, where we might put a portfolio of 1 or 2 or 3 different sulfate remediation modalities together to try to get sulfate to the level that we need it. So what's available? What I've got here, it's a chart that shows both technologies that are in place and technologies that are under development. And I'll just let me get my laser here and just kind of point this out. This is the sulfate levels from very high, 2,000 milligrams per liter on the left side to our state standard, 10 milligrams per liter on the right side. We have here different technologies, reverse osmosis, and then a set of technologies under development. Their relative cost, which is not meant to be not meant to be factual, just sort of a relative measure, and then our differentiators down here. Let me just run through these just really briefly. Reverse osmosis is the gold standard. And you can see here that the dotted lines are supposed to indicate theoretical ability to handle concentrations within this line. The actual ability or the actual utility of these different types of technologies are contained in the solid line. So reverse osmosis is generally used for relatively low amounts of sulfate remediation. The reason that it's constrained such, it's a great technology, but it's extremely technologically intensive and energy intensive. So it costs a lot. This is a commercial reverse osmosis plant, and it definitely will do the job, but it is prohibitively expensive, particularly for places like municipal and industrial wastewater treatment. So given that, we have started to develop other sets of treatment modalities. So these 3, biological absorption, anion exchange, and chemical separation reactivity, are all under development at NRI and at our partner colleagues in other institutions. I'm going to talk about 2 of these. I'm going to start with chemical separation and reactivity, and then move to a biological approach. You can see here that the chemical separation reactivity is a really broadly applicable type of remediation technology. It can handle very large or high concentrations down to and including our state standard. So it's really quite attractive. Also is low to moderate price, which makes it also attractive. I've mentioned these differentiators. I will bring this up occasionally as we're going through here, but just to go through this list, the part of our judgment, of course, and this back to your definition of these toxins, or your practical water wisdom, is that to be practical, they have to be efficient, which means they have to be cost effective. So we always look at whether, first of all, whether a technology can do its job, but whether it can be done economically. if it can't be economical, then it's really just not going to work as a solution. There are huge volumes of water that need to pass through these systems. So we look at whether they can handle high flow rates. There are contaminants other than sulfates in these waters, and so we have to be careful about what comes in and what goes out. Where we get to in a final, or what our final target concentration is important in the way we start to develop the system in the first place. And then there are something that we just call life cycle concerns. For instance, whatever we're putting in to the system is going to come out somewhere, and if that somewhere, and I'll give you an example of this as we go forward, but we want to be able to either use or dispose of in a sustainable way anything that comes out of our system. So we'll have a clean water supply, but what else is coming out and how do we use that? So we consider all these things as we're looking at different technological solutions. The first one, chemical separation. This is some technology that has been developed by Dr. May Kai and her colleagues. It's based on a really well-known, well-established chemical reaction, and it's simply that if you take a sulfate-containing aqueous solution, sulfate in water, and you add barium chloride to it, that will result in the sedimentation, a precipitation reaction that will sediment out solid barium sulfate. That system can be filtered, and the effluent can come out as a clean water. The question is, can this be used, number one, in the range of sulfate that's necessary for remediation? And secondly, is this amenable to actual real world solutions? Well, we start in the lab. Change here. And this is kind of a busy slide, but I'll walk through the important parts. Here's our chemical reaction. This is what it looks like set up in the lab, and we're asking those questions really that we framed up in the last slide. We have, again, municipal wastewater, tap water, and pit lake water, all at the low to moderate sulfate levels, but these are realistic levels. Our test parameters, again, looking at those differentiators, residence time, how long does it take for this reaction to take place? How do we mix it together? What do we have to do to the complex to make the reaction work? Stoichiometry is just a balance of different chemicals within the mixing chambers. Some work better and overload on one versus the other. Of course, in the real world, these things have to operate at all kinds of different temperatures. And then there are, I didn't mention flocculants, but flocculants are just additives that help the precipitation reaction go forward. But there's a lot of different types, and there's a lot of different ways to add them. So these are all questions that we can test in the lab. The results, just to make a long story short, I'm not showing you individual results, but we were able to reduce the sulfate in wastewater and tap water below regulatory levels, and in pit water below 50 milligrams per liter. So very successful, and successful enough to actually take that next step or ask the next question. This works in the lab. Will it work where it counts out in in the environment? In this case, looking at wastewater or industrial wastewater or water from pits. What May and her group did was they took that lab equipment, they upscaled it, upsized it, put it in racks, and then put the racks in a cargo trailer. And then they hauled that trailer to wastewater treatment plants. So this work is, we just call these field pilot trials. started in 2021 and are ongoing at this time. And you can see the hookups here, the hoses running into, so these would be running into a wastewater plant, getting water their influent water running through our system and then back through the plant in order for it to be run out of a permitted facility. We did a similar set of testing on different waters. And these are actual, well, I guess I'd say actual waters. These are, as I said, waters that are from domestic or industrial sources, plus some tap water. Ran these same sorts of tests, got similar results. We were able to find a range of remediation, and which is one of the reasons these tests are ongoing is that we're still tweaking the system. We bring the system back to the lab and do some tweaks on the process, take it back to the treatment plants and test again. Other considerations we look at are this cost. How much does the chemicals cost versus the sulfate we take out? And then the life cycle question. I said I'd bring this back. One of the things that we get as a product of this process is a whole bunch of barium sulfate sludge. And it's kind of, it is sludge. It's muddy. Looks like just orange goop. There are actually some industrial uses for barium sulfate, and we're investigating those. We definitely don't want to dump it out somewhere as another waste product. So that's a work in progress, and we'll let you know. All right, so the second sulfate technology that I want to just cover briefly is the biological sulfate remediation. This is, as you can see from our graphic here, biological remediation can handle very, very high sulfate levels. It is not as practical for lower sulfate levels. So this is one of those areas where we can get back to this again later, but this is one of those areas where one can imagine using a series of remediation technologies, biological, to get the sulfate down to a level where chemical reactivity could take over and move it down to regulatory levels, all in a cost-efficient manner. This next slide showing this kind of shows the guts of the bioremediation. It's actually an electrochemical bioremediation, and you don't have to pay any attention to this other than this right here. These are bacteria or other microbes. There are naturally occurring microbes that will convert sulfate into hydrogen sulfide. That hydrogen sulfide is very reactive to things like iron and will form a precipitate of iron sulfide. So this, once formed, this will just drop out of the water column and be in an inert form. So this is a naturally occurring phenomenon. It's also well known that if you add a current, so here we've got an anode and a cathode and an electric current running between these two, a current produces hydrogen, which actually these microbes use as an energy source, and it accelerates this process by leaps and bounds. So the idea of electrochemical bioremediation, which by the way is being conducted by Dr. Chanlan Chun and her colleagues here at NRI, is to form modules, if you will, that contain the microbes and a food source and an electrical current, add sulfide, add iron, and you can remove sulfate from the water column. So we did essentially the same path. Start out in the lab, and this, once again, no reason to look at details here. This is a picture of the actual device, and this is a a schematic of what's included here. Here's our electrical current. Here's our bugs in the sediment. Make a long story short, here this works in the lab. Will it work in the field? Well, Chanlan took the same series of steps as May Kai did in the with the chemical precipitation, and she put this whole unit into modules and into a trailer, took those out into the field, and in fact, those work too. So I'm going to skip that trailer step and show you her next iteration of scaling up. And that is what we call in situ or in place bioremediation. And in this case, so here's our framework. In this case, we've got our electrodes here and here. And the substrate, instead of being sediment, this is some sort of organic substrate, maybe with some structural elements like limestone to keep things in place. But this is where the microbes would grow. So sulfate water comes in here, moves through the system, and exits here. This is a system, as I said, this is an in-place system. So what we're aiming for is to put some sort of these units, or to build these units right at a pit mine, maybe at the outlet of a tailings basin, and really let nature take its course. Here's a slightly more detailed graphic of what this might look like. And this picture, by the way, is not one of, we're not at this stage quite yet. This is another type of remediation that would, our system would look like this in the end. But here we have pit lake water coming in. We have our medium here, the wood chips, limestone. Here are our electrodes. The nice thing about this, of course, is that we could run this system on a low voltage renewable energy source or off the grid. And then our effluent coming out here as remediated water. To take this one step further, Dr. Chun and her and other colleagues are looking at the next step. I'm calling this scaling way up. In this case, we have our integrated biofiltration system, our electrochemical bioremediation system that is hooked in series with something that is known as phytoremediation. So phytoremediation is, it's an established process by which you take certain plants and plant them essentially in a contaminated site. The plants take up the contamination, and then you can take the plants, harvest them, and process the contamination away from them. It's a technology that has been under development for quite a while. Works in certain situations. We're testing it in this one, and in fact, we have developed some poplar hybrids that grow very fast, take up a lot of water, and we're selecting them for their ability to take up sulfur for this application. This work is being done in collaboration with the U.S. Forest Service and other researchers here at NRI. So now with that, I've got a few minutes left, or maybe I'm just reaching the end of my time. I want to just turn back very quickly to getting away from the remediation of polluted or contaminated sources. I want to get back here just to talk a bit about trying to intercept some of the problems at the start, which is at the mine site itself and at the mineral processing sites. So this set of efforts takes a look at processed water. Some of the problems there are just the volume of water, the chemistry that is involved with liberating the elements of interest and letting the other ones go, and then changes in the physical quality of the water, like pH. In the current situation, Now here's a place where these are sort of stunning numbers. We produce 35 to 40 million tons of taconite pellets a year. For each ton of taconite pellets, we use 10 to 15,000 gallons of water. Now I mentioned that most of this water is recycled already. So this is 80 to 90% of the water in a plant is recycled. The remainder goes into the tailings pond, into waste that has to be treated on site or evaporation. So 89% recycled is a very good number, and the industry should be acknowledged for getting that number to that point. But 10% of a very large number is still a very large number. So we're looking for ways to cut that down. Here's a graphic that just shows a very compressed view of what goes on in a taconite plant. We have a feedstock coming in, we have water coming in. In the plant, there are all kinds of processes that make big rocks into taconite or into iron concentrate. That water is circulated there's the 80-ish%. Some of it is released into the tailings pond. Some of that is recirculated, brought back to the processing plant. But it is in this area, and of course in the area that is in the water treatment area, where we can get leakage, seepage into surface freshwater, which of course is undesirable. Our targets then for being able to address water issues are pretty clear. The water coming in, the water recirculation, and then the water leaving the plant. Our proposed solution, and this is, I have to say that this is in the proposal stage. We have a lot of people working on this and working at different aspects. But I have to say that the industry is very open to these types of technologies, and they're working with us to help develop them. So I think there's a kind of a positive future here. What we're looking at is a future where we have a totally closed loop with water supply in a plant. So water coming in would stay in. So here you see no water input, no makeup water. There are a couple of different ways that we could that this could go. The preferred method would be developing a system so that water is just recycled throughout the plant without any need for any sort of internal treatment. If that isn't quite operational, our second preferred treatment is to treat the water within the plant, but once again have a closed loop and have nothing going out. This is not a preferred option. The purging water out for treatment. What we end up with, we still get a concentrated product, but here's really the interesting part, this idea of dry tailings for dry stacking. This technology is also actually in use in pilot stages and some demonstration stages. Hasn't moved into a widespread use yet, and there are a lot of technological hurdles that have to be crossed before we can get there. But I just wanted to show you that as sort of the positive view of the future, trying to address problems at the source. So my last slide here is just a kind of summary. I want to remind people that we are only addressing this technological section of the living well together. The other sections, legislation, policy, regulation, and the very most important, probably social license, is I think that we're all a part of that in other spheres. But this is what we can address: efficient and affordable solutions for sulfate control, We didn't talk much about mercury and methyl mercury. I think I bypassed that in the looking at the biological control, but we are very interested in controlling those processes, reduce water usage and closed circuits at processing plants, and then changing over the chemical regime for more, let's call them environmentally friendly chemicals that need less processing and less remediation. And then finally, life cycle approaches. I mentioned it for the barium sulfate. Life cycle for all of these processes is incredibly important. We always need to look at what's coming out of a process and saying, all right, so what do we do from that? We don't want to create new problems as we're trying to find solutions for existing problems. It's a different way of looking at things, but we think that it's going to be very effective. And that is where I will end. Thank you very much for the opportunity to share this with you, and be very happy to answer questions that I am able to provide whatever wisdom is still lurking.
Okay, Pat, thank you very much. That is so encouraging, man. Now it's time for the Q&A portion of today's program. It'll be hosted by Bill Granches, the director of the Itasca County AIS program and a longtime member of the Itasca Waters Board of Directors. Bill?
Thank you, Brian. Hello, everyone, and welcome to the question and answer section of today's program. Now, please remember you're going to submit your questions in writing by clicking on the Q&A. You see we have received several questions that way. We'll not be using the chat function today. So I'm going to read the questions out loud, and then they'll be answered by Dr. Shaw Pat. We may combine similar questions together, and we may not get to all of your questions. So please feel to email us at info@itascawaters.org after the program if you still have unanswered questions. Okay, let's start the questions here. First question, Pat. Oh, in your slide regarding barium sulfate, the results were reported as greater than 10 milligrams per liter. Was this correct?
The barium sulfate, I reported sulfate levels.
Okay.
And if I showed barium sulfate, that was incorrect. So I think somebody may have caught a glitch there. That was meant to be sulfate levels. Yes.
Okay, very good. Thank you.
And thanks to the questioner. I'll go back and fix that.
Wonderful. Okay, next question. How are today's water filtration and filtering systems better than their predecessors?
It depends. We've had good filtration systems for a long time. That technology is fairly well developed. Now, having said that, and I can get in a bit of trouble here because, as you're probably aware, I'm not a minerals person. I'm not a mining person. But I do talk to those people, and I know that filtration on the industrial scale is a major problem, or I shouldn't say a problem. It is a major issue when it comes to making sure that we can economically process waters. I think that I'm suspecting that the questioner is actually asking more about maybe consumer level filters. What do you think, Bill?
Could be.
Yeah, I don't really have much knowledge on that. I know that filtration systems are very good. You can actually get a home reverse osmosis system. These are pricey, but once again, they are, as I said, gold standard and really, well, they're very good. I think that the filtration systems that are commonly used, and here again, I'll reemphasize this. It's not my field, and I can't give any sort of endorsement, but it's my understanding that they are good and quite effective.
Sure. Okay. Terrific. Next question comes from John. In northern Minnesota, a lot of us depend on both mining and tourism for income. Tourism depends on clean water, but mining has the reputation of decreasing water quality. How can these two industries live well together? What would that take?
Well, I'm going to go back to my first set of slides with the water in Minnesota. That solution, that overall solution, is going to take a combination of all of the aspects, the technical aspects, the ones that we are able to address, and then the legislative, regulatory, and those might be kind of the same. Regulations are derived from legislation, so that and maybe we just call those policy guidelines or restrictions. And then there is, I've emphasized this a couple of times, the idea of social license, communities like yours. I mean, this group that is interested in this subject and is getting together on a routine basis and talking about hard subjects is very much part of that. The reason I emphasize that so much is that if change is going to come, it is going to flow from communities, community groups, social, economic aspects to the legislators. That will flow to regulators. I have found and this can be contentious, but the industry people that I've talked to in this on these subjects, and I have dealt with in my field as an ecotoxicologist, I have interacted with permitting people and the environmental people in many mining operations, and they're just like us. They are interested in clean water, and they're interested in the entire economic sphere. So I think that my answer to the question is that it's going to take everybody in a particular direction, but I really do think that it really starts with us people, groups like this.
Very good. Absolutely. Next question is from Mike. What are the sulfate let me start that over. What are the sulfate concentrations for proposed copper mining in Minnesota, such as ore and processing discharge?
As far as I know, it is 10 milligrams per liter in areas that produce. Well, I have to be careful. I go back to that actual language in wildlife. I'm sorry, wild rice areas. That therein lies the rub. The standard is clear. Where wild rice areas are is not clear. In the areas that have been explored for copper nickel so far, I think I can say without stretching too far that they are in wild rice producing areas. Other areas that have not yet been explored, we don't know.
Okay, fair enough. Oh, an anonymous question. Actually, this is a good one. What chemical precipitation using barium chloride, with chemical precipitation using barium chloride, can you speak to concerns of chloride release?
Yes, we do measure chloride, and chloride is an issue. That's very kudos to the questioner for picking that up. There will be a stoichiometric release of chloride for every barium sulfate that's formed. Chloride, luckily, is much easier to handle than sulfate. So it can be cleared in usually in a ion exchange column or something like that.
Sure.
So yes, that is, and again, kudos to the questioner for picking up a life cycle question.
Agreed. Next question is from Pat. How soon will these processes be available to used in mining?
Well, that's a really good question. I mentioned several times that about the notion of scaling, and I sort of walked through a couple of scaling exercises. We can do a lot in the lab. In fact, we can do almost anything in the lab that we set our minds to. We can force something to work, right? But taking it out in a real world situation, I think that you saw that in the results coming out of the chemical precipitation out of the lab were very clean. We were able to drive sulfate way down. Take them out in the real world situations, and we get a lot more variability. So this is a way of semi-answering the question that we need to keep tweaking and pushing. We might get to a stage, I mean, I hope not, but we might get to a stage where we just say, this isn't going to work. Because when it gets large enough, now I showed you a couple of those, a couple of figures on flow rates. We were flow rates of a couple of gallons per minute. To do an industrial or a wastewater treatment plant, you've got to add zeros to that rate. Yeah.
Commas.
So these are all things. So I can't answer the question directly about those remediation technologies, but it'll probably take a bit of time. On the mining processing technologies, one of the pieces of good news is that the system, I sketched out that system that our colleague, Dr. Takuta, has developed. His system contains no new technology. It is just pieces and bits that are taken from different places and put together. They haven't been done before, so it's going to take another series of pilots and demonstration tests to do it. But and we right now, as I said, we're at the proposal stage. So and the way these usually work, if we're at the proposal stage now, and if we would get funding for that proposal, you could expect something to be at a demonstration stage where you would have a sort of semi industrial scale in 5 to 7 years. A lot of ifs in there too, though. So that's the kind of time scale we're looking at. So,
okay. Got it. Oh, longtime listener, Karen. Hi, Karen. Who will pay for the sulfate remediations, the mines? And how much slurry can be recovered through, for example, the taconite pellet processing?
Who pays is a really interesting question. And I think, once again, I'm going to go back to that, to my sort of everything idea. Right now, everybody's paying. One way or another, we all pay for processing. We pay in, and this can get sort of twistedly philosophical almost, but we even pay for it in the iron products that we use. We certainly pay for it every time we send out, we have a regulator go and do water testing, things like that. We pay for it in our wastewater treatment bills. And I know that it's kind of a weaselly answer, but I have to say that the more I have gotten into this field of it, sort of on the industrial scale, the more I realize that this is it's a societal issue, and any way we look at it, for instance, if we would make a demand of the industry to remove a given contaminant to a certain degree, they could probably do it. Where would the price go?
Gotcha.
Yeah, so one way or the other, like I said, I realize this is kind of a weaselly answer, but we kind of live in that kind of world.
Yeah. Not very, yeah, okay. We are running out of time. I'm going to try and slip one last question here. Boy, the questions are just pouring in right now, too. I wouldn't be surprised if we get a lot coming to us in email. Are there any tests on mercury and other metals mitigations besides sulfate?
Can you, I'm not quite sure I understand that question.
That's two of us. Well, reading it verbatim, any
Yeah.
tests on mercury and other metals mitigations besides sulfate?
Let me just say this, that the mercury problem, and I didn't mention mercury too much, but it's a good opportunity just to take a last minute to do this. I will say most of the mercury that we have in our landscape did not come from the mines. It has come cross country from coal burning plants in the West. And so what happens is that mercury is spread over the landscape. When sulfate waters, sulfate impacted waters meet mercury, and usually that generates, or that coincides with sulfate metabolizing microbes. When that happens, you have an opportunity for methylmercury to be formed, and that's the dangerous form of mercury. So those three components, water, sulfate, and mercury, where they show up together, that's usually where we have a mercury problem.
Sure. Very good. Well, thank you very much for those questions from the audience, and thank you for those great answers. Brian, I'm turning it back over to you.
All right, thanks, Bill. And again, from me too, a big thank you to Dr. Patrick Schaaf of the Natural Resource Research Institute at the U of M Duluth, doing some fantastic work there. Make sure you register for our next Water Wisdom program that comes up on August the 1st to learn about success stories on preventing and remediating the spread of AIS in Minnesota lakes. If you would like to watch this program again or recommend it to your family, friends, or neighbors, a recording of today's talk will soon be on our website, itascawaters.org, along with our previous programs. And to give us your feedback, please click on the survey link, which will be on screen or is now at the end of today's program. You will also be getting an email evaluation form so you can choose how you'd like to respond. I'm Brian Whittemore for Itasca Waters. Thank you for being with us today.